Hello, and welcome to the Semiconductor Industry Association's public webinar series, where we address current issues impacting the global semiconductor industry and market. My name is Falan Yanug. I'm the Director for Industry Statistics and Economic Policy at SIA, and I'll be host and moderator for today's webinar. One only needs to look around on today's roads and highways to see the ever-increasing presence of electric vehicles. Most market analysts forecast the electric vehicle market to register compound annual growth rates of between 25 to 40% over the next 10 years. In fact, in a recent report by the Boston Consulting Group, they estimate that by 2026, electrified vehicles will account for more than half of light vehicles sold globally. And semiconductor technology is at the forefront of leading this growth in vehicle electrification. The chip requirements for electric vehicles are actually much higher than for cars powered by gas. We are fortunate today to be joined by a group of distinguished panelists for a conversation on how semiconductors are critical to enabling this electric vehicle revolution. Mr. Ray Cornyn is Vice President and General Manager of Vehicle Control and Networking Solutions at NXP Semiconductors, leading one of the longest lasting and most successful MPU and MCU portfolios in the industry. Ray has a comprehensive background in both engineering and business roles. Originally joining Motorola Semiconductors in the United Kingdom, Ray worked as a field applications engineer on microcontroller and microprocessor products before moving into business roles supporting the first 32-bit MCU product lines in automotive. Now based in Austin, Ray is responsible for management of some of NXP's newest automotive products, specifically focusing on the drive for high functionality, safety, and quality for today's complex automotive systems. Hi, Ray, and welcome.
Hey, thank you.
Mr. Mike Kulchin is a fellow and GM of the Automotive Battery Management Systems Group at Analog Devices. Mike has been designing integrated circuits for automotive, aerospace, communications, and industrial applications for 37 years. During his 24-year tenure with Linear Technology and ADI, Mike has contributed to over 45 products, including battery monitors, amplifiers, monolithic filters, and silicon oscillators. Currently, Mike is General Manager for ADI's battery management products. He holds 6 patents for his work. And prior to Linear Technology and ADI, he worked for Ford and Motorola. Mike earned his BSEE from the University of Missouri and MSEE from the University of Texas, Arlington. Welcome to you, Mike.
Well, thank you, Fallon. I'm really happy to be here.
Perfect. Finally, Mr. Saeed Ahmed is Senior Director of Vehicle Motion Segment at Infineon Technologies America. Saeed Ahmed has been leading the electrification and powertrain business in the Americas at Infineon Technologies for over 15 years. His team is responsible for marketing automotive products in electrification applications, inverter, onboard charger, DC and battery management systems, as well as traditional ICE applications, engine, transmission, transfer case. He has over 20 years experience in the industry, both in engineering and marketing roles. Saeed started his career at International Rectifier in California and worked at EcoStar, Electronic Drives, Ballard Power Systems, and Fairchild Semiconductor before joining Infineon. Saeed holds a PhD from the University of California, Berkeley, and an MBA from the University of Michigan at Ann Arbor, and has been awarded 10 US patents. Welcome to you, Saeed.
Yeah, thank you very much. Great to be here.
Ray Cornyn of NXP, let's start with you. NXP is a leader in the controller and processor space, especially for autos. Tell us how your work in this area is particularly critical to enabling EVs.
You going to share my screen now, Falan?
Yep.
Your screen. Thank you. So, Falan, thank you for that introduction. What I'm going to talk about today is mainly the development of vehicle architectures and the new microprocessors that are getting developed along with that new technology, and how that will assist and help to drive the technology in electric vehicles. Could you change the next slide, please? So a little bit about NXP. NXP is one of the largest suppliers into automotive. It's actually, for those of you who don't know the history, it is the combination of Philips Semiconductor and Motorola Semiconductor. Philips is very well known for its background in consumer plus connectivity plus security, and Motorola with its long legacy in automotive processors. In fact, I think some of the very first microcontrollers in the automotive market came from Motorola. all now part of NXP, and today we lead the automotive microprocessor market. Not the only market that NXP works in, very strong in industrial and very well known for our security systems, especially in the mobile marketplace. We're headquartered out of Eindhoven in the Netherlands with about 29,000. Next slide, please. So today there are three main dynamics driving the automotive market. Today we're mainly going to talk about electrification, but safety in the form of ADAS and autonomous drive and the connected car are some of the other major factors driving the market and the technology. But fundamental to all of those new drivers, there's also a change happening in the underlying vehicle architecture itself. And part of that involves a move to much higher performance processors, which also assist and help in the driving of some of the new requirements for future electrification. Next slide, please. So if you look at the way that the automotive has developed over the last 20 years, we went from very simple vehicles with maybe a little bit of electric content to today where the average number of processors in a vehicle in 2020 was about 45. Now, to put that in context, that is the average for all vehicles globally. So that includes some of the smaller vehicles from emerging markets, along with some of the higher spec vehicles from Europe, the US, and Japan. So if you actually look at this in terms of a higher-end vehicle in any of those higher-end markets, you're actually talking more about 90 or even 100 processors per vehicle. And that comes with 100 to 200 million lines of code. And shockingly for most people, connecting all of those modules together takes about 1.2 kilometers of copper wiring, which actually adds to about 75 kilos of the weight of the vehicle. So as we go forward, that started to lead to a number of issues in automotive. As you try to integrate software together from about 100 modules, it becomes a real challenge. There's actually a couple of vehicle platforms that have come late to the market over the last couple of years because of that complexity. But also in terms of the complexity of building vehicles with so much wiring, what that's driven towards is a couple of significant changes coming in the market that are changing the architecture of the vehicle. So we're not seeing a complete reduction in the number of ECUs, but we're going to see that growth reducing as those modules become more and more powerful. But we're seeing architectural changes which will simplify and reduce things like copper wiring and weight reduction. So next slide, please. So what we're seeing at the moment is two significant architectural changes in the vehicle. Today's cars tend to be very flat architectures with based around CAN networking, which is a specific automotive standard. What we're seeing in terms of software is a move to much larger, more powerful computing domains. So you're seeing previously 10, 50 modules now being integrated into a single module with much higher performance. And this allows a higher integration of software together, easier updates. And historically, if you wanted to add a new function to a vehicle, you almost always ended up adding a new module. With these new platforms, you can add features, even retrospectively to vehicles, taking advantage of the new computing performance that you're getting in these new domains. Now, in addition to that, there is a parallel change in architecture, moving away from the flat architecture that we have today to more zonal architectures and more hierarchical networking. So instead of lower speed interfaces, you're now seeing vehicle architectures based around about gigabit Ethernet and even higher frequency data transfer mechanisms than that. So you're seeing this change both in the software platforms that are getting developed and in the networking architecture of the vehicle. So next slide, please. So what you're seeing is, and this is a representation of those new computing domains that we're starting to see develop. There's not a standard across the industry. This is an example Sometimes you'll see some of the vehicle networking and infotainment being combined. Sometimes you'll see that being combined with body and comfort. But the top three areas are the areas fundamental to the vehicle. And these are the things that make, there's commonly the comment of, well, are modern vehicles not just becoming smartphones with four wheels? Well, that isn't really the case, because you're still talking about maybe a 2-ton vehicle traveling at 100 miles an hour. It's the control technology that is in there for the vehicle is more like a modern aircraft than it is a cell phone. So you're seeing these areas of up integration. And the ones that we're really focusing on from my team at the moment are both the vehicle propulsion side and the vehicle networking side. So now I'll talk a little bit about vehicle propulsion, domain control, and how that is focused on some of the new requirements for electric vehicles. So Flan, next slide. So on the left, you can see a diagram of a propulsion domain controller. And this one is basically being, it's a diagram for a hybrid vehicle. So you've both a combination of traditional combustion plus new electrification. And what's happening there is a lot of the previous functions that were in standalone controllers are now getting up integrated into these propulsion domain controllers. So all of the strategy and some of the new strategies that you need for electric vehicles are now appearing in those propulsion controllers. On the bottom left, you can see a diagram of a number of the functions that are now getting up integrated. And these are all functions aimed at improving the efficiency of the vehicle. And that's one of the reasons that these propulsion domain controllers are getting much, much higher in performance. I mean, a traditional microcontroller for a gasoline or diesel engine might be a 300 megahertz microcontroller with 3 or 4 cores. A full propulsion domain controller that's been developed today is potentially 8 ASIL-D cores running at 1 gigahertz. So it's a massive increase in performance. And that's to allow you to run all of the modeling functionality you want to run for these modern vehicles. There's a term you'll see there, there's a term called GLOSSA, you'll see there, which is green light speed advisory, optimized speed advisory. And that's an algorithm that can be run in the domain control system to ensure that you get the maximum efficiency out of your electronic control system. But it doesn't just stop there in terms of performance and functionality actually inside the domain controllers themselves. On the right, you can see a demonstration system that we built with Amazon Web Services, where not only do we provide a significant amount of performance in the green box, which is our domain control demonstrator system, we worked with AWS to bring in cloud computing. So now not only are you running algorithms actually in the vehicle itself, you're also taking advantage of the significant amount of cloud computing that is there for the future of the vehicle. So this is a great demo. It allowed us to show the combination of advanced battery management, motor control, and the connection into the cloud to take advantage of all those services that you can get from cloud computing. So next slide. So that's a very quick summary of what we are working on in terms of advanced domain controller for electrification. The 3 areas we're mainly focused at from inside NXP are battery management, electric motor control. But for my own team, our biggest focus is in this new generation of very high performance domain control to improve the efficiency of the electric vehicle and take advantage of those new architectural changes and help drive those architectural changes that are coming through overall. Well, and that's where I was going to finish that introduction.
Perfect. Thank you, Ray. I appreciate that introduction. And yes, obviously, new semiconductor innovations and technologies enabling electrification is quite mind-blowing. Mike Colchin of ADI, I kind of wanted to ask you the same question about Ray that I asked Ray in terms of the microcontroller space, but instead regarding battery management. Obviously, one of the defining and distinguishing features of EVs compared to internal combustion engines and cars is their use of batteries instead of a tank of gas or diesel, right? And this is a technology where ADI obviously is a leader. can you tell us a bit about battery management systems and EVs and Semi's roles in enabling them?
Right, great question, and leads me into a topic I love dearly. Can you share some slides for me, please? And we'll go forward one. Like Ray, I'll just give you a little background on ADI. We're a 55-year-old company, about 16,000 employees worldwide in many markets. Very powerful in communications, industrial, automotive, which is about a sixth of our business. And in the automotive area, we focus on electrification of the powertrain. So the battery is a big focus for us. The digital experience, which means the in-cabin experience, premium audio, road noise cancellation, and then autonomous mobility, where we have some unique technology and inertial MEMS sensors. But focusing on battery management, let's go to the next slide, please. I always like to start these things, these kind of talks with what is battery management. I think a lot of people have a rough idea, but in an EV, it's about a third or a fourth of the cost of the car is the lithium-ion battery. There's roughly 100 cells connected in series, 104 volt cells to create a 400 volt high power source of energy. So each one of those cells has to be measured and balanced to ensure safety, for one thing. When lithium-ion batteries catch on fire, they're impossible to put out. They produce their own oxygen and fuel, so it's quite a unique situation. Also, for range, for charging, every cell must be monitored for voltage, current, and temperature to get the best state of charge estimation. And of course, the better you do that, the more performance you get out of your vehicle. So the battery management system is a collection of ICs that monitor all these individual cells, as well as total pack voltage, and communicates that data to the microcontroller, where there's critical software algorithms to make sure we know what the state of the battery is. Every cell has to be balanced, because if one goes out of balance, then the pack is limited by the weakest cell. So you want to have all of them reach their end of charge at the same time. And data communications is a big deal within the pack, because all this data must be aggregated. It's a high voltage system, requires isolation, certain level of bandwidth, and reliability. And as I mentioned at first, I mean, overall, the thing has to be safe. So the electronics are what ensure that we meet automotive safety integrity level D, which is the highest in the industry, and that's what's demanded in EVs. So what ADI brings to the party is these measurement functions. We have a long history, 6 generations of parts, where we've refined this technology over the years. It's a very difficult problem to solve. Measuring a 4-volt cell running on top of 400 volts of common mode, and measuring that down to a millivolt in the presence of a lot of noise, and doing that repeatedly is quite difficult. And cars last for 15 years, so we can't allow the electronics to degrade over that time period. And as I said, this impacts the user experience greatly. So for adoption of electric vehicles, we want no range anxiety, so the longest range. We want to be able to recharge quickly, and we want that vehicle to be on par cost-wise with a conventional internal combustion engine vehicle. And as the technology is improving, and as Fallon mentioned, but by 2026, the price will be on par or below ICE vehicles. The range has been extended to levels where you don't really have to worry that much, except for maybe long distance trips. and recharge time will keep coming down and down. So battery management enables this adoption. One more slide, please, Val. But it's not just the car where battery management comes into play. There's an entire circular economy around batteries, right? So, a battery reduces greenhouse gases, but the overall carbon footprint, is only low if you reuse that battery as much as possible and if you manufacture it in a green way. So we look at the entire ecosystem, the entire circular battery economy, and try to apply our technology in all these spaces. In cell pack manufacturing, if you look like at a Tesla Model 3, for example, it uses 4,000 small cells a day. Per vehicle. And if you make a couple thousand cars a day, you may need to produce 10 million cells a day. That's a significant manufacturing bottleneck. So if you can bring electronics to bear on that problem, improve quality, reduce the manufacturing time, it's a big benefit in the ecosystem. Vehicle assembly, if you can enable a wireless battery pack, you take out a lot of the headaches with cable harnessing. You make the car very configurable. We bring wireless technology to the problem and really enables OEMs to scale their fleet. And of course, vehicle operation, the BMS, as I've said before, increases range, reduces charging time. An accurate BMS actually enables a lower cost, higher performance chemistry, lithium iron phosphate, which contains no cobalt, which is actually a conflict mineral, and reduces the demand for cobalt and nickel, which may become harder to find in the future. Reuse of batteries is going to be important in the future as these vehicles come end of life. There's still quite a bit of capacity that battery could be repurposed for grid storage, and grid storage makes green energy sources way more efficient because you can store wind energy at night, redeploy it during the day. And batteries also improve the grid. People worry when everybody has a car, will the grid be able to sustain the charging? And in fact, if all vehicles today were electric, we'd need about 25% more capacity on the grid. One way to get more capacity is to deploy batteries as local storage sites, so we can charge our car during the day and recharge the storage on the grid at night. So these are the ways that the semiconductor technology is it's impacting the vehicle, but actually society in general, and making the world greener, which is a goal of ADI and a really rewarding facet of this business. So thank you very much.
Thanks, Mike. And I definitely want to underscore that point you made at the end about how, not just semiconductors enabling auto transformation to EVs, but also, as you mentioned, just transforming society. And I think your last slide was very illustrative of that. So that was very, very important to underscore. I appreciate that. Finally, Saeed Ahmed of Infineon, your company, Infineon, is deeply involved in the automotive space in a number of areas, but especially power. I'd love to get your thoughts on how semiconductors are critical in generating powers in electric vehicles compared to internal combustion engine vehicles, and more broadly, just connecting the dots between EV technology, applications, products, and of course, market factors, right? I think you're on mute, Saeed.
All right, can you hear me?
Yes.
And the slide is okay?
Perfect.
Okay, good. Thanks, Falan. Appreciate the invite, and I think this is a great session. Thanks, Ray, for setting the stage for the vehicle architecture level. What are the things we need to do for EV? And I think NXP is definitely playing a great role there. And Mike, you really did a great overview of the BMS. Is not just from the BMS perspective, but more broadly, not only automotive, but also the whole life cycle. I think That's really great. What I will discuss is the inverter application, which essentially takes the power from battery and then converts it to the AC power that is needed for motor drives. And we at Infineon, we are in the inverter is one of the key area that we are focusing. So I will first before going to the inverter, I'll also give a brief overview of Infineon as a company. So Infineon is about a $10 billion company. I would say two key messages from this slide. One is the automotive is our major focus. As you can see, almost 50% of our revenue comes from automotive, and we are a major player there. The second point Falani already mentioned is that Infineon has a long history of leadership in power semiconductor that we from automotive, industrial, and in the consumer market, and we have about 20% market share in the power semiconductor area. And from a historic perspective, Infineon came from Siemens as a Siemens Semiconductor division. It was spinned off in 1999. So I think since we are very focused on automotive, let's look at our core beliefs about automotive market. And it's no surprise, I think it's very similar to what NXP also mentioned, that our core beliefs is one of them is the zero CO2 becomes real, and driver becomes a passenger, which is more on the ADAS and autonomous space, and the car becomes a smarter car, which is more on the body and infotainment area. Obviously, the first core belief is very much connected to the EV revolution. And as you know that on the EV side, we have been talking about for a while, I would say, but now the revolution really started. So to make this revolution successful, actually, rapid progress is essential in multiple areas. Battery, as Mike described, it's not just battery management system, but battery itself, charging infrastructure, and also semiconductor is very much connected to all of those. And here we are here to speak about how the semiconductors can play a key role in this revolution. So let's look at the key factors that Infineon is focusing on. And what I want to mention is that there are these three essential ingredients for this EV revolution. And I will describe beyond the technical side, also some of the market need and how Infineon is addressing those areas. So as you know, the automotive industry actually is not fully prepared for this EV revolution. Most of the OEMs, tier 1 and tier 2, are still not there what is needed. And the three major hurdles are these, and one already Mike mentioned, the system cost. I think this is definitely needs to be at par with ICE engine, and I think most of the OEMs has a plan, but let's see how we can enable that. The second point is actually very important, is the faster time to market. I think, as you know, the most OEMs are scrambling how to launch multiple vehicle platforms within short time. Development cycle is shortening from typical 5 years to 3 years, and even 2 years. And the third point is, as you know, if you talk about automotive, you cannot escape the chip shortage topic, right? So we all know about the present bottleneck of in the automotive production is the semiconductor. And as each of the panelists mentioned, the semiconductor content is going to significantly increase in the EV. How should we take care of the supply security to really make this growth reality? So these are the three topics, and I will explain how specifically for inverter application and power side, what is Infineon planning to do in these three areas. So inverter, just a brief technical description is that, it's the inverter basically is the bidirectional, power conversion between high voltage battery and the electric motor, right? So one side of the transfer of power is from the battery to motor, also the regenerative braking to a battery. And of course, at the end of the day, inverter powers the motor. So that's where the vehicle motion goes to that. Let's look at the application in a little bit more details. And as you can see, there are a lot of components to make an inverter. And one of the key feature of Infineon is that we pretty much play in every area. Microcontroller, memory, power supply, gate driver, power stage, of course, and sensor area as well. So we are a kind of a all supply for all the components that are needed there. So in essence, what we need to understand the interaction between the components, and what we look at is like, okay, how do we really address the system cost, not only from one component, but from the whole system point of view. And that's where our goal is to reduce the inverter system cost by utilizing all the levers we have from all these components. Before we go into details, I think let's look at a bill of materials for an inverter to just see where can we make the most impact. And this is a busy slide, but I would like you to focus on this part where is the, more than 80% of the inverter BOM is actually bill of materials is the power module. And this is where I think we need to, this is one of our focus. And of course, as I mentioned, we are utilizing microcontroller sensor and ASIC and other products as well to look at it. But power semiconductor definitely is a key part for making this car affordable. So let's look at the inverter in terms of the technologies. What are the power technologies for inverter application that we can see? Of course, silicon is the most common, and as you know that we are transitioning from silicon to silicon carbide, and GaN has a place in the overall electrification, but maybe not inverter in the near term. But the main point I want to bring is that since Infineon is investing heavily on the power technologies, we have all these technologies in-house. So we can see which one to use in what applications so that we reduce the kind of cost. Just to give you an example on silicon carbide, that's I'll focus our activities in that space. The Infineon developed a very trench technology for the silicon carbide that actually I want to give you some explanation. How do we reduce the system cost? We look from the design perspective. The chip design wise, we need to make sure that it's the most efficient chip from the power conversion point of view. The question is how is this technology helping us to reduce system cost? So if you look at our, let's say our Gen 1, the silicon carbide 1200 volt device, to Gen 2, we reduce the on resistance by almost a factor of 2. What it means is that first of all, if you use the same chip size, you are going to reduce the loss by almost 50%. And to just complement what Mike mentioned about the battery range, I think BMS plays a big role, definitely, but also inverter can play also a big role in increasing the range. If you increase the efficiency of conversion, that means that your range will be a lot higher. So that's one part. The other part is that, okay, if you want to reduce the chip size and try to keep the same loss, that's where definitely the cost reduction plays a role, because the smaller chip area means lower system cost. So we are not only looking from the design technology point of view, we are also looking from the process or manufacturing technology. So silicon carbide, as you know, is a very expensive material to start with compared to silicon. And we are trying to reduce the waste to improve the material efficiency. So typically you have this 4 centimeter crystal that comes, and then traditionally today, most of the companies are doing sawing. And sawing means you are really losing some material, very expensive material. And for a 4 centimeter crystal, you can get about 50 wafer in this present system. We acquired a company that does have this what we call cold split technology, where you don't do the sawing, you do a splitting, and that's where you don't reduce this, you don't have this loss, so you actually improve the number of wafers from 50 to 100, and we are in the process of making it reality by 2023. So as you can see that by reducing the material consumption, we are also kind of increasing the number of chips you get from the same bowl. That means you are actually reducing the system cost. Let's have a look at the second factor, which is also very important, like faster time to market. From the inverter point of view, we have long experience. We have about 20 BEV platforms in production, and if you look at the top 25 top selling EVs, 17 out of 25 is run by Infineon power device. So we shipped about 18 million modules of different shapes and sizes, and we actually have no field failure. And that's we learned through this last 10 years how to really make it very reliable. And this is where the quality and other factors comes into play. But the main point, what I want to highlight here is that we went to the learning curve. So when we work with our customers, we can really reduce their time to market because we have already gone through this experience. So that's one part. The second part, as you know, that if you look at one vehicle platform, there are multiple vehicles, and some of them needs low power, some of them needs higher power. For example, if you look at the truck versus car. And what we did is looked at these customer challenges and said, okay, how can we help customers to have a scalable platform, scalable portfolio. So we offer the same package, but you can go from 120 kilowatt to 250 kilowatt. You can do silicon and silicon carbide, same package, also 400 and 800 volt. I can tell you that one of the customer wanted to launch their vehicle in 2 years in both silicon and silicon carbide. We are able to give a package that serves their need, and that way we also reduce their development time and also their validation time and cost. So this is an important part to make sure that the customers can reduce the product development time. Let's look at the third factor, which is very, very important. Is right now, if you look at the EV number of EVs in the market, and in 2026 or 2027, the number of vehicles is increasing significantly. And even in this production, low number of vehicles, we know some of our customers facing major challenges in the supply of the IGBTs or silicon carbide MOSFETs. And imagine when the penetration is going to be increasing by a factor of 5 or so. And so I think what we are really actively working in this area is a global multi-sourcing strategy, so that we have multiple suppliers for silicon carbide bowl or wafers. And then also we are doing major investment. We already did major investment in in-house, front-end, and back-end manufacturing. This is very important because, as you know, in the present the situation with the automotive chip shortage, this is a major problem, that when you are depending on some external partners, you don't have in control. So we are making sure that we are in control of the front end and back end manufacturing, we are investing 2x more than other players there to make sure that this power semiconductor shortage is not an issue. Also, we are doing this dual front and back end side to provide robust supply. As you know, in this pandemic, we learned that that you have to have multiple sources to make sure the production doesn't stop because of some certain situation. Also, we have about 40 years of experience in the manufacturing of power devices. Those are also helpful. So I think let's summarize how Infineon is enabling the EV revolution from the power semiconductor perspective. So first of all, what we call it that dependable electronics comes from multiple key factors. One is this system cost reduction. So as I have seen the trench technology and the cold split technology, Infineon is very much innovation and technology focused. And the goal of the technology is to reduce the system cost. And also the broad product portfolio, you have multiple products in this application, you have more levers to play. So we are doing that. Faster time to market, we have a lot of field experience and great quality. That helps to reduce the time to market. And also the scalable products helps you both from the design and the timing point of view. Supply security, in-house manufacturing with major investment in the both in IGBT and silicon carbide side, and also dual front and back end manufacturing facility. So in summary, I wanted to bring not only some of the technical factors, but some of the market factors that are really needed to make this EV revolution successful. Back to you, Falan.
All right, thanks, Syed. And I appreciate you raising a number of very interesting and important points, especially challenges on the supply side to make this EV revolution happen, which I'd like to get back to in the Q&A, which will be starting now. I want to remind folks, if you do have a question, please go ahead and submit it in the Q&A written submission box at the very bottom. Just click there and submit your question. I see we have a couple questions come in, but I'd like to loop back to you, Ray, with an initial question, sort of along the lines of the challenges that Syed has raised in terms of and what companies need to do, right, to make to enable and supply and provide the right environment for making electric vehicles happen. But I want to talk on the technological side. What do you see? You talk a lot about sort of the overall architecture. What do you see as maybe a potential challenge on the technological side, on the chip side, in terms of needing to be overcome in order to keep sort of the electrical EV revolution sort of moving? You see anything in the future that would be like, aha, we got to be careful, or we got to look out for this technological challenge or barrier that's coming up?
There's not, I wouldn't say there's a single barrier that's there. I mean, getting that last piece of efficiency out of battery technology and motor technology is critical, and that's one of the reasons we see this huge growth in computing power required for some of the calculating power that's needed for the algorithm. So I think we see a good roadmap to continue that. One of the interesting things actually for automotive electronics is obviously automotive is a fairly difficult environment. I mean, if you're beside electric motors, they're hot and noisy. And obviously electric vehicles now have the ability to actually, especially when you talk about things like robotaxis, be on for phenomenal amounts of time. So we're doing a lot of work on that long-term reliability in terms of if you have electric vehicles that are now going to be running 24/7, does that mean you have to look slightly differently at your reliability models? So that's some of the things that come in, but a lot of it is about ease of use of processing power to get the absolute maximum out of the system capabilities. Because even very small percents improvement in battery efficiency or electric motor efficiency really improve the range of the vehicle, and that's the thing that everybody still has, all the anxiety about.
Right.
you know, as you said, I live in Texas. It's although lots of people have electric vehicles, it's a very big state. And so there are still a few limitations there that need to be overcome. But I think I don't see something in the near future that will be that aha moment. I think it is a good understanding of where technology needs to go and how quickly we need to develop it in that direction.
Yeah, no, I appreciate that. Definitely, I think, well, you know, with Moore's law and just the semiconductors continuously evolving and innovating, I think certainly I feel good, at least in terms of on the chip side of the continuous innovation that will help enable sort of this progress. You mentioned, and I want to ask you about this, Mike, because it has something to do with you know, sort of batteries and sort of you know, sort of the range anxiety question that Ray mentioned. And that's regarding the infrastructure, right? You know, we see charging stations here and there pop up. You know, in my neighborhood, I saw one in our grocery store garage. All of a sudden, I was like, "Oh, that's a sign of the times," right? You know, but still, obviously, way less sort of charging stations around that infrastructure. That would, I suppose, compared to obviously, you know, gas stations, that would sort of enable people in their minds to say, now I can, I'll take that leap, right? I feel comfortable that when I'm commuting or I'm going somewhere, I've seen enough charging stations that I won't feel, you know, stressed out about, you know, having my battery sort of, you know, sort of go down. What's your view in terms of just that the infrastructure and how that's going to evolve and how that will enable or any challenges on that side?
I think the proliferation of charging stations could be helped a lot by some government initiatives. You've seen that in other countries. The grid itself is well capable of supplying EV charging today, but if 100% of the cars were electric, we would need about 25% more capacity on the grid, which is doable, especially if we augment the grid with local storage. And you know, one of the, I would say, positive effects of the pandemic is it's kind of been a morphing of how we work, live, and play. And with more work at home, there's a little bit less range anxiety. And with the extension of the battery capacity, where you're going to get a lot more range, this range anxiety is rapidly coming down. So, and again, I too notice way more charging stations. Mm-hmm. So as the fleet electrifies, I think naturally there's a lot of business opportunity to have charging stations. It's a revenue generating scheme. And then I've also been involved in some groups that are looking at wireless charging as you drive down the highway, as you park in shopping malls. There could be underground chargers just there that would supplement the plug-in charging. So.
Is that a sort of like charging as you drive? You're driving and all of a sudden just...
It's technically possible.
Okay, wow.
It's a little scary to me. There's that much electromagnetic radiation coming out of the ground, but it's certainly possible. Or if you think about all the stoplights in the city, maybe you come to rest at a stoplight, and for 2 minutes you gather some small amount of charge. I mean, these are all things that we should consider when we're designing new cities, new downtown areas, new highways. Mm-hmm. You know, as revenue from gas tax goes down, how are states going to monetize this? So like the state of Missouri is looking at electrifying some of the highways to try to regain some of this revenue that they're going to lose from gas tax.
Yeah, wow.
Things are coming down the road. Very exciting.
Very exciting. Yeah, I agree. Totally exciting. Saeed, and I guess I wanted to switch over to the Q&A and hit some of these questions before the end of the hour, because I think they're quite interesting. One question that's come up is the question about you know, you mentioned the current chip shortage and what that means in terms of how customers, auto customers to chip companies will need to secure the needed supply that the wing needed, because obviously EV sounds like, you know, there's going to be more chip content, going to be more need for supplying chips, but also how are our customers going to be sure that they have a secure amount of supply? And obviously one of the issues that has been raised with the current auto chip shortage has been the use of just-in-time inventory on the part of customers. maybe that needs to change, maybe so any implications that you see, especially moving to EVs and the higher content of chips per car and just the need for more chips to ensure between semiconductor customers and semiconductor suppliers and auto customers to be sure that there's a guaranteed supply, and that with this increased demand from customers, by 2026 we have 50% of the light vehicles on the road are EVs. How do we be sure there's no disruption in supplying that demand?
Right. I think this is a major challenge that we are going to face if we don't actively work on it. As you know, the present situation is not the electrification chips, it's just normal chips that for combustion cars, we are having this problem, right? So I think one of the key part, I would say first, is to really the OEMs and tier 1 and tier 2 to understand each other's, supply chain, like how does it work? I think we have, and the demand volatility is another challenge, right? I mean, we understand that the, let's say OEMs, accurately predicting what they will need is sometimes challenging for them. But I think what we are working right now is to say, okay, what are the potential demand that you have? And we need to, communication is a challenge. A lot of time, customers are ordering, okay, I need chips like, 50% more, but, our cycle time is long. The investment cycle time is long, and also the manufacturing time is long. So I think this capacity, we have some program that we are working with customers that they can secure what the demand in a program that reduces the risk from our side, also from their side. So actually, this is a very interesting situation that OEMs did not think it through that much before, but now they are understanding that they need to be just-in-time delivery. It doesn't work for semiconductors. It needs our chip factory needs to be very highly utilized, 90%, 95% to be efficient. But we cannot change the production suddenly without having those equipment ready. So I think this is continuous dialogue that is going on right now is very healthy. But we need to come up with a approach that serves the need of the OEMs and tier 1s, as well as semiconductor constraints that we have. We need to address it.
Okay. Ray, Mike, any comments on this?
I agree with Syed. It's been the kind of just-in-time manufacturing system that has worked very effectively for many years in automotive has really got a shake-up to what effectively happened over the last year, and I think that will have to be looked into. But as I said, the problem in semiconductor, it's a long manufacturing cycle. It doesn't do well with sharp either upturns or downturns.
Right.
And I certainly see the car OEMs now wanting to and understanding more about the complexity of that supply chain. So I can see a lot of very constructive ideas starting to come in about how we help that stability of supply going forward. But it is honestly amazing that it has lasted so well for so many years. We've had little blips over maybe the last 10, 15 years, but this is the first one that's really shown that system has a certain instability in it as if you want to call it a control algorithm that needs to be resolved. So yeah, but there's a lot of focus from the OEMs, the tier 1s, and the semiconductor companies to ensure we get back to a stable supply for the industry.
Yeah. We have a number of other questions. I'm just going to throw a few out, and if you folks can pick and choose, but just want to get a few other things on the table with the time we have. One is about how long will it be before we have solid state batteries? Also, to a question I think is interesting, curious what kind of fundamental basic science developments might be necessary to support and realize the EV revolution. And then a question about memory, I guess, memory content in terms of what is needed in terms of EV on the memory side. I know cars don't necessarily use a lot of memory compared to other sort of end markets and devices. But anyone want to take a stab at any of those questions?
Sure. On the solid state side, the technologies there, we got to figure out how to scale it up to be economically feasible. I think you'll see early adoption as early as 2023, maybe the first application of solid state. But to really get there, we need large scale manufacturing that's as cost effective as the current technology.
Yeah, cost seems to be often a challenge with developing any new technology, I suppose. So how about the question about memory? I guess that I know, as I mentioned, cars compared to other types of devices on the market that are enabled by semiconductors don't necessarily use a lot of memory, but does that change when we talk about EVs and moving from gas and diesel powered to EV vehicles? Does the memory content change at all?
I mean, maybe I'll mention one part is that, even in the combustion engine now, people are this over-the-air update kind of situation is becoming a standard, and that's needing some memory. But I think on the EV specific, I would say maybe, Mike, battery area is one area that people, and people are learning what's the information you need in the battery cell to make sure you monitor and like thermal runaway situation, and what are those. I think there are some AI activities that are needed in those kind of situations. With battery is the most sensitive part there, and also other inverter and charger. There memory actually is becoming a more need in future, but I think it's still in the evolving stage for the EV specific stuff.
Gotcha.
Ray, you wanted to comment something?
Yeah, I would say I think you're right. It's not, although EVs require some additional computing power for some of those advanced algorithms, actually I think it's the overall development of the modern car architecture that drives more of that memory growth. And certainly as there is more and more software being added to all vehicles, you will see that continue to grow. So I don't think it's specific to electric vehicles, but it's modern vehicle architectures are using more and more memory as the functions get more complicated and the software becomes more involved, or the software moves to higher level than traditional microcontrollers up to more microprocessors. So that overall change, which is actually one of the things you see appearing first on electric vehicles, but it will be in all vehicles, because that fundamental architecture change is good for combustion as well as EVs. It's not specific to those. They just happen to be at the forefront.
I agree.
Cool. Well, I know we have other questions, but I wanted to ask one last question in the last couple of minutes we have of all three of our panelists, more out of curiosity than anything else, because I myself do not own or have driven an electric vehicle, but I've heard that the experience is quite different from a traditional gas or diesel powered vehicle. And from folks such as you who have are not only just helping to make this revolution happen, but I presume have driven or even may own electric vehicle. What is from the driver or the passenger experience? We talked about this whole transformation of it's still on 4 wheels and it's still a vehicle, but it's completely different in so many different ways. Just a sense, like what's from your point of view the really cool thing about EVs that people should know about, and maybe even something about that cool thing that is enabled by a semiconductor that makes it happen. Can we go around?
I'll go first because I think the same maybe others will pick, so I'll go first with the acceleration. Okay, and so acceleration is just this amazing acceleration, so you cannot get it in the regular combustion engine. Okay, sorry, I took it first.
Can I expand on that one and say it is the ease of that performance, because you can get combustion engines that give huge amounts of horsepower and can almost match, but the ease of that torque and the ease of just makes so attractive for users, because it doesn't mean when you've got a combustion car, if it's going to put out that amount of power, it's going to make a lot of noise. It's so usable in terms of electric performance. And it's the usability that we all really want as drivers. We want that instant torque. We want to be able to accelerate into a gap in traffic. It's total usability. And that's what the amazing attraction, even in the lower powered EVs, is the same. So it's that usability performance.
Mm-hmm.
For me too, when you step on the pedal, you will grin ear to ear.
Absolutely.
Really?
The other thing is the modern EVs, it's like the difference between today's smartphone and the old phones of the past. I mean, the integration of all the things in your life that come into the cabin, that's possible in combustion engines as well, but just the new way of thinking. And as an engineer and a geek, you just like, oh, that's so cool. All the different things. So it's a whole mindset that's different and new and really exciting.
Yeah. Well, man, I really want to, maybe this weekend, I'll see if I have time to do a test drive of one of these cars, just go, maybe not buy it, but still this whole idea of the acceleration has me sort of interested in trying that out. And your point, Mike, I like that comparison, like who would go to a flip phone now, right after having a smartphone? Again, it's all, there's so much power and so much functionality that you have in a phone. And if that is the case, when you compare, sort of the traditional, internal combustion engine experience with EVs, then man, that will be a whole new revolution in terms of how people experience driving, right? So I'm that this is and I suppose if the predictions and forecasts are right, this is not very far off, right? 2026 having more light vehicles being EV than internal combustion, it's right around the corner, I suppose. So I know we're at the top of the hour. This has been a very exciting topic to talk about, and want to thank you all for joining us. I really appreciate Ray Cornyn of NXP, Mike Kulchin of ADI, and Saeed Ahmed of Infineon Technologies. Again, appreciate you taking the time helping us understand and explaining this wonderful technology, and maybe we'll catch up in about 5 years and we'll talk about our EV experiences. So appreciate it again. Thank you very much.
Thank you.
Pleasure.